So I'm going to review my notes and I'm going to try to clarify some things. Mainly one thing, which is just the stack offset. So I'm probably going to open the executable that comes from the Flare challenge. Then try to find an example where they put something on the stack. And then I'm going to open another executable that doesn't have any code. Or that is just from a course that I did, which he shares this executable just as an example for you to put some code. And I'm gonna try to see if I can copy the code that they use there to put stuff on the stack, to do some experiments to see if I'm understanding how the stack offset works correctly, which is something that is is one of the most confusing parts so far, and there are other parts that are still confusing to me, and I'm probably gonna try to clarify this another time. I'm just waiting to see the streaming. I'm not really sure if I'm gonna be able to put the code there because I don't remember from the course how he did it, so it might take some time, and yeah, I'm not really sure if I'm gonna be able to do it now. But so this is basically the notes I have so far. So yeah, local variables grow to lower addresses, and parameters grow to higher addresses. So parameters are put, I think, before on the stack, before the return address, maybe. I'm not really sure. And the local variables, so but basically what it means is that every time that you see a plus offset is probably a parameter, and every time that you see a negative offset, then it is a local variable. Because yeah, obviously the things are going to be put on the stack based on the RSP, which is the register that keeps track of the stack address. The Microsoft compiler is always trying to maintain a 16-byte alignment. So based on this I saw from the OST video that I watched again, which is probably, if not the best, one of the best courses that I've seen so far. It's basically this course here. Actually, it's not from this channel. It's from OST. I'm gonna try to find. Basically, all their courses, they have their course. There's some of the courses that are different on their website, and but it's basically, I think that it's just two versions of the same course that they just updated. But yeah, I think that doing both on the site and on the playlist very good. That's probably the best courses. The course on architecture is also extremely good. So I might do this course again actually because it's so good. But I think that it might be better now to investigate the keywords that I already have here because obviously he goes into that, but not that deep into each topic. So I think now for me is probably more the time. But I'm probably gonna watch the course again actually because it's very good. But based on this, that this Microsoft compiler tries to maintain a 16-byte alignment, I realized that it's just obvious that like on the 64-bit system, each row of the stack is going to be 8 bytes because 8 bytes are 64 bits. And on the 32 bits, I assume, I haven't tested it yet, but I assume that's going to be 4 bytes each row on the stack because that's what it means to be 64 bits, as far as I understand right now. And that means that the reason why it's confusing is that there are 16 values there, and the reason why is because each hex is 4 bits. So 16 multiplied by 4 is going to be 64. So it's just representing 8 bytes per row using hex, and that's why you have 16 squares there. That's a very confusing part. But I'm pretty sure that's how it works now. Because if you copy the value here, go copy either address or keyword, and the name says keyword as well. Uh, I think it's extremely likely that is 8 bytes because a keyword is 64 bits, a D word is 32 bits, and a word is 16 bits. And just basically based on the way that the architecture has evolved, because the highest value on the register, because of technology and how the size of transistors and stuff like that, initially was 16 bits, and that's why 16 bits is a word. Then they jumped to 32 bits, and that's why it became a double word, and now it's keyword, which is 64 bits. And that's the reason why as well that you have like the same register, you have different names for the same bits on the same register because of the evolution. So EAX is like the 32-bit equivalent of the RAX, which is 64 bits, and it's just the lower bits. This is like the convention. So there's every time that a function calls another function, you're gonna have the caller, which is the function that is doing the call, and you're gonna have the callee, which is the function that is going to be called. So there are conventions, but this is one of the parts that I'm not 100% sure how it works. But this is basically the registers that are supposed to be saved by the caller by convention, and these are the registers that are supposed to be used to save values from the callee. And this is basically the responsibility of the compiler because that's like it's not embedded into the hardware, this structure, because it has to be an abstraction on top of the registers. So it's like a convention that the compilers use when they are translating code from C++ or C to assembly. And basically every other language, because everything is going to be compiled eventually into assembly, because assembly is just the machine code. So like the Ben Eater is very good for this, the Ben Eater series. But each assembly instruction is actually a collection of microcodes. And microcodes is just like the specific operations that the CPU does, each part of the cycle. And that's why some instructions take longer than other instructions. So, for example, I'm not so sure about the details, but like let's say you want to move data to RAM. It might take 2 instructions, which is to move from the counter to the register, and then from the register to RAM. Or if you want to move data to the ALU or some other parts, it's going to take other amount of instructions because each time you're moving the signal from one part of the computer into another part is like one cycle on the clock. So each micro instruction is a microcode, and the collection of the instructions is going to be the thing that is actually hard-coded on the instruction set architecture, which is the assembly instruction. So just predefined instructions arbitrarily created by the hardware designer to serve as an interface or API between the software and the hardware. So this playlist is very good for understanding the microcodes. On the final videos, it talks about the microcodes. But this part I don't understand very well because like a lot of times coming from the higher level programming languages, it's very common to have like a bunch of different arguments, and then you have a bunch of different local variables as well. So I would think that in a lot of programs, the amount of local variables and parameters is going to exceed the amount of registers you have available. Also, given that they might be used by other operations that came before. But it might be the case that it's just like because it's a different way to think about it. Because like on the higher level programming languages, it's like an illusion what you see because obviously it's just abstracted away. So it might be the case there's just extra steps that higher level programming languages usually do. And then this creates the illusion that you're gonna have the same consistent data. But what's actually happening under the hood is that sometimes the compiler is gonna use the register to put the values on the addresses, and then it's gonna take them later or put them on a stack or whatever. But it does feel kind of weird, because there isn't too many registers and the values have to be saved each time. So yeah, I'm not 100% sure about this. So I guess like just with experience is gonna be more clear what's going on. But the other thing here, first four parameters from left to right are put into the RCX, RDX, R8, 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 R9. Remaining pushed onto the stack so that the leftmost is at the lowest address. Typically, move is used instead of push, though. Yeah. So it's just on the reverse order that they are put, I think. So it starts with the right and then goes to the left. I think this is the same on the local variables, like or the way you put the structs. I think it's structs on the stack or something like this. That is like on the reverse ordered in the way that you declare that they're gonna be put on the stack. This is another interesting thing that I've seen. I don't remember the name of the guy or the channel, but it seems like the bitwise end is the same as modding, and mods is just taking the remainder. But mod is very confusing, so I'm gonna have to review this again at some point. But it's basically this formula here. So the examples to give is if you want your mod to take the bitwise with 1. If you want your mods 32, take the bitwise with 31. So it's basically this formula here. The mod of 2 to the power of x is equal to the... You just take the ends with the 2 to the power of x minus 1. So there's just going to be 1 minus, yeah. It's just like the formula says. If you want to take the mod of one number, and you're just going to take the bitwise end of the number with whatever the equivalent is. And that should be a multiple of 2. So let me see if I can find the... I think it's competitive programming. It's basically this video here from this guy that he talks about this. Very good video. So this depending on which kind of jump you use, it's either going to be unsigned or signed. So it's just like it says. So jump below or above is unsigned, jump greater or less than is signed. And this is one of the parts that I'm not 100% sure, that I'm kind of confused here. But it seems that the hardware doesn't care about whether the value is signed or unsigned. It just does the operation and then sets the flags. But I'm not, like, I've seen this on the video, but I'm not 100% sure what this means, because in my mind, the operation would change depending on what kind of number you have. But I think that the way that it happens is just that it's going to take the binary value. So like on assembly is going to be the hex value on the register there. But on machine code, it's probably going to be the binary value and then just the bits. And then based on the control logic or the logic gate structure, which also this is something that I was slightly wrong since last time that I said this. The ALU is going to be an XOR and an AND gate. So, and I think it also has a carry, but I'm not 100% sure. But it's basically doing XOR with and then AND gate. So basically all the operations are going to be probably through that. And yeah, so I'm going to have to research this more. So I'm probably going to search for... So I'm putting the stuff that I still have to clarify on this column here, and the notes that I have here, and then additional notes that are complementary to this one on this one. I'm probably going to have to see... So does true complements happen on the hardware or on the... I think it happens on the hardware, because I don't remember really well. So yeah. Because if it happens on the hardware, then it means that the hardware is gonna be able to know that it's signed or unsigned. Yeah, so I'm not 100% sure about this, but I'm gonna clarify. So this is another thing is the XOR is used on encryption. So this is why, and I think the XOR that I was seeing here when I was studying before is on the part where Windows is going to be loading the DLLs for the process and it's going to be setting up the process. And what it does is something, it randomizes the addresses. So in order to do that, it uses a assembly function which is called rand, I think, to generate a random number on a register. And then it XORs that with another register. And I think it does that in order to make sure that the number is going to be random each time. But I'm not 100% sure if that's the reason why it was doing that. So this is the one that I'm trying to clarify now. Just basically when you sum a value to the RSP, how many rows can I calculate on the stack that is gonna go up and down? And the reason why it's confusing is because if you have, for example, if you have hex 10 on code, is gonna be equivalent to 16 decimal, because you just take the value and you multiply that by 16 by the power of the square that it is. So the first value would be 0 times 16 to the power of 0, which is 1. So it's going to be 0 times 1, which is 0. And the second one would be 1 times 16 to the power of 1, which is 16. But the problem is if you're using hex 10 on, and this is the part I'm not 100% sure, but ChatGPT also agrees with this, but I'm not 100% sure yet. But I think it's probably the case. But if you're using this as a size, then it's going to be equivalent to 16 bytes. And this is the thing that is kind of confusing to me. So when you see on the stack, for example, RSP plus, I think you can have both. Actually, it's going to be just a number, because when you have hex, it doesn't say anything about, it doesn't do the 0x, so just doing the number here. So for example, here when you do RSP plus 8, I think what this actually means is that it's increasing the RSP by 8 bytes and not 8 decimals. Which obviously, if it is like that, then it makes a lot more sense. Because obviously it would be increasing the stack by 1 row. But this is the stuff that I want to clarify now to make sure that it is the case. So this other thing is if you want to keep track. So I saw an answer on Stack Overflow, because the question that I have is, let's say I get an address here on a register and this value is put on the memory dump, and I want to see what happens with this value later. So this is the question that I had. But the answer that I got from Stack Overflow is about following the register values, but on the memory dump instead. So in order to do that, you can go here, click sync with expression, and then you put as ESP, which is the register you're tracking. So I guess you can put any register you want to track. But I'm pretty sure that you can put the address as well. So, but I haven't tested it, but I'm gonna test probably. Not sure if now, but probably sometime. But I guess if you put the address, then it's gonna allow you to just follow what happens with that address each time that you execute. So this probably solves this, but I'm not 100% sure. So this one is the 8 bytes per row that I explained. So it's 8 bytes each row, so 16 there because 8 times 8, 1 byte is 8 bits, so 8 times 8 is 64, so 64 bits per row. You divide by 4 because each hex is 4 bits. So 64 divided by 4 is going to be 16. So that's why there's 16 values on each row here. Yeah. And this is the other keywords that I was talking about. So I'm not, from what I understand right now, the addresses on the process are going to be virtual process addresses, the addresses that show up here. Those are the addresses that are going to be randomized for each process based on this address space layout randomization. And this address is going to be translated into a virtual page. The OS is going to do that. So it's going to have a, so the way that I'm thinking about it right now, obviously I'm not 100% sure about the nuances, but the way that it's gonna happen is that the OS for each process that gets instantiated, the OS is gonna communicate. I'm not really sure if it does communicate with the kernel, but I think probably. And then the kernel keeps track of the page table, which is just like a hash map, where you're probably gonna have the index of the process, and that's gonna map to its virtual pages. And so it gets translated from the virtual process address into the virtual page table, and then from the virtual page table into the physical address. And the way that it translates from the virtual page table into the physical address is going to be from memory, using memory management unit, and this translation look-aside buffer. And also, in order to deal with the caches and the synchronizing caches between multiple different processes, there's two different strategies. If I remember, one is all the processes use the same bus, and then they just send the message each time there is a change. They send to all the other processes, and then it synchronizes that way. But the problem is that that's not very scalable. And the other one is using a directory approach, which I don't remember really well. But I think it's just like you have one process, or you have one directory that keeps track of multiple different processes. It's kind of like a store, and it's kind of like a context on React, where the directory would be the context, and each process would be the thing that subscribes to that context. So you send the signal to the centralized thing, which is the directory, and then the directory manages the synchronization between everything. I saw this on our video, on our sure I'll just say his name, but very good videos as well. So I'm pretty sure that I saw one of his videos. And the name for this, the convention here between caller and callee registers is procedural call linkage. So I'm going to search this later as well. So now I'm going to just follow the execution here. And I don't want to, I want to find a place where, oh, so this is another thing. A lot of the times you're going to see this subtraction on the RSP, and it's because of the 16 bytes alignment. So you have to keep as a multiple of 8 the stack each time. So depending on what happens on the execution there, on how many variables parameters you have, the compiler is going to subtract or add values to the stack. But I think it's mainly subtracts in order to keep the alignment. And the name of this is shadow store, I think, which is probably something that I'm going to look more into as well later. So what I'm going to do here is just try to find, so I guess I can copy this example. Because I think the beginning there I'm going to have, which is just the beginning of the stack frame, just pushing the RBP. No, not really because it's very confusing. But I think it's RBP. RBP is the base pointer, and EBP is just going to be the first 32 bits of the RBP. So I think first you push RBP into the stack, then you push SBP into RBP. Yeah. So you push RBP into the stack to keep track of the address from the last function call, I think, and then you push RBP into you push RSP into RBP to move the stack pointer to the address that is on RBP, which is the beginning of the stack. Then you subtract to give space to the shadow store, and then probably you deal with local variables or parameters, and then you do whatever the function is gonna do. I think that's the stack frame, and then obviously at the end you're just gonna pop everything and then return. So, but I think I can just look. I'm just gonna copy this one. So I wanna look into some examples. If I can't find anything, I'm just gonna ask ChatGPT, obviously, and then I can just try it out and see what happens. But I wanna see, like, I'm gonna push two random values into the stack just to verify that the thing here is correct, and then I'm gonna do it with hex as well to verify that it's correct. But I'm pretty sure it is. I'm just doing this just to make sure, to see if I understand how it works. So I guess I can just test this one. Because the thing is that there might be differences because of the. So this is another thing to test. So what happens if you push on a size? I guess this is the like you can push. Like what matters is the place you're pushing at has to be like a line, let's say, because otherwise you run the risk of overriding other values. But I imagine that the size of the stuff that you're gonna push doesn't matter as long as it's lower than 8 bytes. If it's longer, then it's gonna be the same problem, which you're probably gonna override other values. Like you run the risk of overriding other values. I'm just gonna see if I can find another example. Oh, the other thing I have to test is the sync with the address there. Well, after I do these things, I also like this is kind of the thing that's another thing that I'm kind of struggling with. But I'm not really sure if there is a very good way to deal with this. But I assume that's I think that it has to. I'm gonna see if I can find like because I think it's gonna be very hard to find information about this about what are usually the values used to manipulate the addresses because it's gonna be specific to each thing. So to each process, each stuff that you're gonna do. But for this stack, I think it's obvious that it's going to be always like the same values because obviously you always wanna put the parameters and the local variables right after the return address, I think. Or like after you push RPP, which is the return address, and then after you push RSP, you're gonna put the parameters and the local variables. But I would say I was gonna say that you're gonna put them around, but I saw a video as well that's and this is another part that is confusing. I guess it goes into the procedure called linkage. Is that because of these conventions here, I think that the caller is responsible for putting the parameters or dealing with the parameters, and the callee is responsible for the local variables. So, but I'm not 100% sure about this. I think it depends on the. It's gonna depend on compilers, definitely based on the registers, but the relationship between the parameters and the local variables is still not 100% sure. But you find like a standard or like addresses that you can practice the translation in your mind from the hex into the to have an idea on your mind on how first on the magnitude of the sizes from like the beginning of the process into the last address on the process. Like this is always going to be standard. The relative size are I know they're going to be standard, but yeah, but the numbers are going to be specific, but the range is going to be standard. So like to have an idea of that size and to have an idea of how when you see these operations being done on hex here, to understand roughly where they're gonna move the original thing, and that's very hard to do, I think. So this is kind of what I'm struggling with. So I think the stack one is easier because it's most likely always gonna be similar numbers, but for the heap, I think it's very hard to imagine based on the hex you're gonna see here and the values on the register, like how to derive meaning from them. So here, for example, these are plus, so go to lower, so it's probably parameters. So I think the convention is probably gonna be that the caller deals with the parameters. I think that makes more sense. So callers deal with parameters and the callee deals with the local variables. That's probably how it works. So here what's doing is pushing the values on these registers, which are the parameters, probably to the function. But actually this is already after calling the function. So this should be the callee. So the callee is, yeah, but it doesn't make a lot of sense. I guess it might depend on the convention there. But I do think that's what is happening here is that it's pushing. Sure. I just realized now that I should probably write the values on the registers as well. But I guess the values don't matter that much. But what I'm gonna have to do first is move the values into the registers, and then move the values from the registers to the. I guess I can look here as well. But this is gonna be the. Maybe it's not the value of the instruction. I think it is the value of the stack, the one that highlights there. So RSB plus 8 should be this one. And it is. RSB plus 10 should be. It's confusing because it's 10, so you immediately think on decimals, but I think it's probably a hex. So it's like 16 bytes. So it goes from 8 to 10, and like it makes you think that it's gonna be in the middle of the next, but it's not because it's just 1 byte lower. So what is RSI? Yeah, RSI is 0, so it should be 0. This is why it's kind of hard to figure out. I'm gonna copy these instructions here, but I'm pretty sure now that it is what's happening just based on the example there. I can already tell that it is what is going on. So when you see a decimal value here, it's actually has the hexadecimal is a hexadecimal value and is talking about byte, not the decimal of the hexadecimal, if that makes sense. So 10 is actually hex 10, which is actually 16, but it's not 16 decimals, it's 16 bytes. And that's why it's very confusing. A copy from here. And I'm just gonna do another value on this one, like because it's 0 there. I think, but I'm gonna copy here. But I'm pretty sure, yeah, it is 0. So I'm just gonna copy this one, put here, and then I'm gonna put some other stuff. The thing is, like in order to overflow the value, you should probably you would have to use you would have to do the wrong operation on 2 different places because the register is going to limit the size as well. I'm pretty sure that the value of the register is going to be 16 hex, which is going to be 8 bytes as well. Each register, yeah. The register is 8 bytes, the REX. So the maximum value of each register is going to be 8 bytes. So if you want to override the, like, if you, in order to overflow the value of each row on the stack, you would have to push to the same address on 2 different operations. I'm just going to put a bunch of apps here. I maybe should just put, or it should not be confusing. I'm gonna remove this. So I guess I can dance with these values and then just do the minus as well, but that probably doesn't matter that much. And the push, as far as I understand, is just gonna be, it's gonna do under the hood the operation. So it's gonna put the value on the stack, and then it's gonna decrease the stack pointer. So it's just gonna move to the next row. As far as I understand, yeah, it's pretty much what is happening there. And it's the same thing that happens with the RIP, is that each instruction the CPU is gonna do under the hood is gonna move the value of the RIP by each row there. But I think RIP is 4 bytes for to move the RIP. And this is another thing that's kind of confusing, but that's why there's some differences between jump instructions. You can have jump short and jump near, and it is because obviously in order to do the operation you need the bits to tell the address. But I think that this is not very relevant usually because the size of the code is not gonna be as big as the size of the data. I think I would assume usually that's what happens because obviously in order to fit the text of the instructions is not gonna matter that much. So I think it's probably it doesn't really matter. But the address in which you can jump to, how far you can jump, is obviously gonna depend on the register that is being used to perform the jump operation on the RIP. Because every time you jump, you're just gonna be changing the value of RIP based on the label, the address you have on the jump. So now, so now I think I can open the other one and then test just if it works. I'll have to remember. I'm pretty sure now. Oh, the problem is that the executables are 32 bits. Hmm. See if I can find one from the project that is 64. I guess it would be like the same thing. It might be even better to do it with the 32 bits. I'm pretty sure that there isn't. So I'm gonna open the 32. I'm gonna test on the 32. As far as I understand, the 32 is also simpler. The instructions. I think it's simpler just because of the variance of the registers. So 32 is not gonna have the same registers. So I think I've there's a problem that this one seems that it has things there. I'm not really sure if it's gonna work because I think it should move. This is a really problem. So I just delete. It's gonna be EBX. I'm gonna delete the zeros. I'm just gonna put a bunch of I think. It's not yes. And the values don't matter that much. You just see where it's gonna be on the stack. But I'm gonna have to do minus, I think. Maybe it doesn't matter that it overrides there, but so now I copy this once. Hmm. It's because of the. I wonder if I can do. Let's do keywords. It's gonna be ESP. Hmm. So maybe if I just do the value, I think the square brackets, as far as I understand, should dereference the value. So like you pass the address and then it gets the value. I think, rather than sure. On the instruction there, I'm 100% sure that it's gonna move the value on the. It's gonna move the RSP to the next. Not sure if it's the next row, but it's gonna move the RSP. So I guess I'm just gonna ask ChatGPT. If I don't get response, I'm just gonna search. I say move ESP. Value use of GPQ. Oh, it's because I'm using the RBX, not the EBX. Yeah. And now I'm not really sure. Okay, yeah, so it works. So I wonder if I put, yeah, so that should be the word because 32 bits. So I think I'm not really sure. So I guess I'm just gonna ask here as well. I'm pretty sure it does, but it's kind of confusing because it's gonna take the value on RSP and it's gonna sum that by the offset, and then it's gonna dereference that, and then it's gonna move the value on the register through that value. But what does that mean? But I guess like the value you get when you dereference is the value of the stack on the address. So you're just gonna move the value into the address. Well, the question is, would it make sense to move directly without dereferencing? Like, what would happen if you did that? I guess you would get a kind of like segmentation file because the address wouldn't exist on the range of the stack, the range available, but I'm not 100% sure. And it's like doing the reference in C, so or C++. When you do the pointer and you do a value of a variable, say, and you do plus plus, both the pointer and the plus plus are they are resolved, let's say, from right to left. So in this case, this one would be resolved first, which means you would increase the value of the pointer, which is this thing, which is the value of the address of A, and then after that you would return the previous value and dereference the previous value. So like when you're iterating over an array, it moves the pointer to the next value on the array, the next address on the array, and then it dereferences the previous index of the array. It's used all the time. So I think it's similar on assembly, but you use the square brackets to dereference. So when you do the offsets inside of the thing, it's kind of like a similar thing. But instead of incrementing, you're just changing the value of the pointer, and then you're getting the value. Yeah, so like it's the same. It's like basically the referencing. So I think it's probably the same thing actually. But instead of getting the previous value, you get the current one. You get the new one. Yeah, so you increase the value of the address, and then you do reference, and then you get the value of that place, and then you update that value. So I'm pretty sure that's what's going on. So it's like it would be like pre-incrementing, I think. But I'm not 100% sure about the post-increment. I'm 100% sure that that's what's going on. But if you pre-increments, I'm not 100% sure. I think what's going to happen is the same thing, but it's going to return the new value. Well, actually, maybe not. No, yeah, I think that's the case because the pre-increment it returns the new, the value after you increment, and the post-increment returns the value before you increment. So what happens here is that you move the pointer and then you will return the new value because you're dereferencing the new value. I think that's what's going on. So you would be like doing that, I think. Yeah, so I'm pretty sure that's what's happening. Yeah. So I think that's probably all I have to do. Not sure why it's not going. Okay. I think it does more than one instruction every time they press F7 or F8. So it did update the values, I think. So I think it worked here. So it's putting here because before the return, because the stack goes down. So higher addresses are actually below on the stack, and negative or lower addresses are on the top of the stack, and higher addresses are on the base. So when you increase the stack pointer, you're actually gonna put on below the return. It's basically what is happening. So I'm pretty sure now that this is what's gonna. So this value here is the same on the EBX. Yeah, so it basically puts the values there. So it's putting this value here. It basically overwrites the overwrote the other value, I think. No, maybe not actually. So this one, I'm pretty sure it is there. So ESI is all F's. So Y is here. This is interesting. I'm sure, I'm 100% sure that the location is correct. Yeah, because it even changed this to A, obviously, which A is 10 in decimal. So A is the hexadecimal equivalent to 10. Yeah, actually, no, I don't remember if I. No, because, yeah, it should be 16, actually, 16 bytes. Hmm. So maybe this is because of the 32 bits. This is kind of weird, because I'm pretty sure that I put, as I can do again here, just copy. Because it should be 16 bytes. So if it is A there, then I think it's gonna be increasing by 10. Hmm. Which is different than 16, obviously. So I guess if I do this, yeah. So now, so maybe it was the wrong thing there because I put the 10 in decimal there. You converted it into hex, which is A. So you went to the wrong place. So I think you overwrote or it didn't go. You, but it should still be like one row below, obviously. If it's 10 bytes, it's gonna take the first row and then 2 bits on the other one. Yeah, but I think you overwrote the value here. That's the other register had. Yeah, so you overwrote the previous value. Interesting. So I guess when you have an overflow, it's gonna overwrite the bits before and not puts after. I think that's what's going on. And here's 14, but I think it's supposed to be the hex again because I put 20, so hmm. This is kind of weird as well. Because I think that 14 is not 20. Like 20 decimal is not 14 hexadecimal. Well, actually, it is because it's 16. I was confusing you with binary. Oh, it is. Yeah, these conversions are very confusing. So, like, I think the part that is the most confusing is doing the math. So, and this is, but I'm not 100% sure how to go about doing this. Like, I'm thinking about creating the Anki cards to do this, to train somehow, but I'm not really sure what values to put there. But basically, what I'm trying to become better at is like having a range on your mind of like what happens when you add two hexadecimal numbers. And overall, beats Boolean algebra overall is kind of confusing as well because it doesn't map directly to normal algebra. Like some operations are similar, but they are not the same as well. So I also wanted to think about this one, like what it means exactly. But modular arithmetic is kind of confusing as well because you take the remainder is like a very confusing way to write stuff. Basically, the notation is very confusing of the mods. And also, like, I'm not 100% sure about what is the actual significance of this formula here. Like, why is that the case? That's the part that is hard to figure out. It's the same thing with the XOR. So now I understand, like, in XOR, it toggles the bits when you use a mask. A mask is either going to be the same amount of bits that the number has, but all zeros or all ones, I think. And then it's just gonna toggle. You're gonna get a new value with the toggled bits. N is also used for encryption, like I said, but like to derive the meaning of what is actually going on the binary numbers, it's kind of hard. So I know that XOR is for adding, so it's basically the same thing as adding. But why is that the case is the thing that is confusing. I think it's just because, like, obviously it's gonna flip the bits. If one of the numbers is 0 and the other one is 1, then is 1. It's like adding the bits. I think you need the AND for the carry. So that's what it means, but this one is kind of confusing. I have to spend more time thinking about it. So now, let me see if I just... I'm not really sure how it works here. I guess it's gonna depend about how... So in order to make it more clear, I'm gonna have to go over... So this is what I'm thinking about doing as well, like going over the notes to have this in my mind, then create Anki cards, and then go over the execution of the executable there to see the patterns on the executable, and then remember the nodes, then go back and forth to put the stuff on like into actual context of what's going on. But it might be better to just select another or create another executable from which basically I have from the project here that I'm writing notes. I wrote the function prologue here as well. Just remember, this is basically the project that I use. I'm probably gonna use as well to use the compiler on Godbolt to study the patterns on how the patterns on C are translated into the. Yeah, I was trying to look into the malloc or into the address. Basically, this stack offset is gonna look into the here. But I stopped in the middle to study other stuff. So push the base, then subtract for stack alignment, 32 bytes. Then push counter register to base. Counter usually contains the first argument to a function. GS segments usually point to the thread information block. So you have the process environment block, which is, and this is specific to Windows, if I understand correctly. So the process environment blocks the standard way that the Windows is going to deal with processes. It's going to allocate a certain amount of virtual memory, which is the virtual addresses of the process. Then the beginning addresses are going to be for kernel stuff. Then you're going to have threads, and you're going to have some additional information on the processes, I think. Then the Windows is going to use that information to communicate with the hardware and just synchronize multiple different processes in the cache and also the virtual pages. And then it translates basically the virtual stuff from each process into the actual physical address through this flow of information. And the CPU is going to have the multiple different threads, which are going to be which the compiler, both the compiler and the hardware are going to try to maximize the order of the instruction, or maximize the executions per cycle and minimize the latency, which is how long it takes for the instructions to be executed. And the bandwidth, which is just the transformation or the transfer of information from one part of the CPU into the other. So it's going to try to maximize that by reordering the instructions in a way that maximizes the hardware architecture, the efficiency, and is going to try to maximize the work that it does for each process and for the multiple different threads of the process. So let's say, for example, you have goes back into the microcode stuff. So if you have one instruction that takes 3 cycles to complete, and you have another instruction that takes 1 cycle, if you have one thread executing the instruction that takes the 3 cycles, you can go to the another thread and execute the instruction that takes 1 cycle. That's concurrency. So you're switching the context between threads in order to maximize the amount of work you do on the clock. And the way that CPU does that, it has some control logic, which is the bits of information that are going to be synchronized through these different parts of the hardware architecture to do the work at the same time. And then you have parallelism, which is going to be just the execution of multiple threads at the same time. So, yeah. And I think most of the control logic stuff, or the stuff related to the control logics that you have access to with the operating system or with the processes you create, are going to be done through bit field registers. Just a fancy way to say that you're going to have a register that each bit on the register is going to be a flag for synchronization of these processes. So that's the descriptor tables. So I think you're going to have that both for segments. I think segments don't exist anymore, but I think for compatibility, there probably exists something like this, like the segments on the processes for the Windows point of view or for the operating system's point of view. Each process environment block is going to have some flags to deal or to organize the different segments of the process that are going to determine what each information from the process is going to be located at. And then you're going to have some other register that allows the operating system to map the virtual pages from the processes into the physical address through these keywords here: memory management unit and translation local site buffer. So I think I'm gonna stop now, and probably another time I'm gonna continue to. Yeah, I'm definitely gonna continue to do this. So I'm gonna study some of this stuff. I think next time I'm just gonna create the Anki cards. That's probably what I want to do next. So probably what I'm gonna do is just open the executable from the Flare-On challenge there, and then follow the execution a bunch of times, and then try to. Yeah, I'm not really sure actually if I'm gonna. Maybe I'll watch videos or read articles on stream to clarify this stuff here as well, because I want to do these things at the same time. I want to go over the instruction on the actual executable, and then put that into context by reading more about these standards from the compiler. But I think probably for understanding the standards, it's probably better to just use this thing here. So probably the best thing to do is just use ChatGPT or Perplexity to come up with simple algorithms or simple stuff you want to do based on the concepts you have. Which I'm probably gonna save on this repository as well. I took some from Jason Turner's videos and some simple libraries. But I'm probably gonna do this. So like put code here on C, get code from ChatGPT maybe, and from Godot as well, I think. I'm gonna write down the concepts, I think, that I want to reveal. It's gonna be probably something related to threads. It's very interesting. I think it's stuff related to the kernel and the Windows and the operating system in general. It's probably better to just change the options here to stop on these different breakpoints, because then what's gonna happen is that what happens by default if you only have this entry breakpoint set is that it's gonna stop. The first breakpoint it's gonna have on the debugger is gonna be the one that comes from the actual code from the executable. so the code that people wrote. But if you put the other, if you mark the other options, then what's gonna happen is that's gonna set the breakpoint way before that, when the operational system is creating the logic to create the actual process. So I think probably I think the best thing to do is to get examples based on concepts and then write them here, then compile them here using CMake to get the executable here. Then with this executable, open that on x64 DBG. And you can also generate assembly. So the flag, I think I can remember from Godot that I put there the flag. But obviously it's easier to search on or just ask ChatGPT. But when you're using CMake, you can use the set and the CMake environment variable. And then here basically you pass the variables. But in the example that I got, I think I got this from ChatGPT as well. These flags here are for when you're using GCC or Linux compiler. If you're using Microsoft, it's going to be another flag. But probably what I'm going to do is just find this other flag and generate the assembly both here and on the debugger. I think that's the best strategy. Then, so like organize everything by concepts, then create the examples with ChatGPT, test the examples on Godbots, then put the examples here, then compile them, create the executable here, and create the assembly here, and then also put on the debugger. Then go back and forth between the debugger and the assembly that's generated by the compiler here, and keep track of the context here. Then use all of this stuff to generate the Anki cards to train the fundamental principles and most important patterns, which I think, just based on the experience I have right now, the most important thing to understand is the stack frame. I think that's by far probably the most important part, because the pattern is going to repeat all the time. And the second most important thing is going to be the relationship between the buffers and the heap, the memory management on the stack. So both that, and then obviously the nuances about the, which is the main thing that I'm going to focus now, I think. Nuances of the memory translation between the virtual addresses on the process and the actual physical addresses on the hardware. And also threads as well. So I think those things are the key things to focus now. And yeah, like I said, I'm probably going to try to link this to Godot. So I might take examples from Godot next time. Yeah, but I'm going to stop here. So next time I'm just going to dive deeper into both assembly, try to merge Godot somehow, or like study Godot and assembly at the same time. It's probably better. And do all this stuff that I talked about here. And I think that it's probably better to do this than to, I think writing the code here is good because it forces you to think, but I think initially it's probably better to just do this whole process here, because it's going to make it a lot easier to have like a decent idea of everything. Then maybe later on is probably a good idea to use this template, or to generate another executable that just like has a simple template. Use the debugger to put a breakpoint, and then do the stuff that I was doing here to write this stuff on assembly. Or maybe use, I think it's probably easier to just use the compiler here. I'm not really sure, or I can search for another one, I think, online where you write assembly, or just use NASM. NASM is the assembler, like one of the main assemblers I think everyone uses. You're just gonna use, it's like a compiler for assembler, basically. You write the stuff on assembler, then use NASM, which I think compilers already do. When they're creating the object file, I think that they use the assembler, and then they use a linker to link the object files. But it's just basically taking the assembly codes and transforming that into machine code. So yeah, probably I can use this later. And there's also the emulator, which is MU, which is also another, but I think that's far more. One of the things that might be interesting is just put the Godot executable there, but I think it's going to be very hard, because obviously it's going to be extremely complex. I'm not sure if it's a good idea, but maybe after I do this all these things, I'm going to put the Godot executable there to see how the execution looks on the debugger. But at first I wanna probably do like a bunch of this other stuff so I get more familiar with the fundamental principles and then I can expand on that. That's basically this program here. Yeah, so I'm gonna stop here. Next time I'm gonna continue to do this. So see you then.